Now we will see some basic important approaches that are bagging, random subspaces, and random forests, which are really well known and used methods. Ensemble methods. So bagging is, I would say, one of the first ensemble approaches where we train each classifier on a slightly different data set. So basically, we have an initial training set, which is the X here. And we want to create an XJ here that is, in fact, a random drawing with replacement of n data in X. So the size of XJ is the same than the size of X. The size is n, big N. But we can get some samples in two or many copies, while some other samples will not be present for a given training set XJ, which is a good way to somehow enforce create data sets that are diverse, still not necessarily having any other impacts on the distribution of the data. So the replacement allowed to get several copies of some data and the absence of some others. And that should be ideally applied in a case where the basic classifiers are unstable. That's funny to say, but because usually we don't want such a thing to be unstable, but here the instability is a feature. So in the sense that for slightly different data sets, like the one we just created with bagging, the final classifier can vary a lot, can be quite much more different than the basic models we had before, which is I would say require, which is in fact logical if we consider that we want to get some diversity in the models we are creating. So this is what we want for unstable. Example of stable algorithms, those who are not varying that way. We have k-nearest neighbors. We have all this kind of parametric classification where everything is relatively stable. And we also have unstable approaches like multilayer perceptron, which is a reasonable approach that can be used for that, or art condensation, where we just apply some routine to prune the training set of our k-nearest neighbor. In general, unstable algorithms have a large variance, but that's okay because we know that with Ensemble, we are reducing the variance. So this large variance, it will be kind of damped down by the fact that we are building an ensemble. And there is a variation of that. So here for bagging, we were talking about sampling with replacement data. With random subspaces, we are in fact rather sampling subsets of features of our problem. So that can be all at once. We just sample different subsets. And then we train each of these models with different subset of inputs. So it's more having, I would say, different views on the same data. That also work reasonably well. All this, we say that we need unstable algorithms. And one very common algorithms in the 1990s, when this kind of ensemble approach emerged, was decision trees. Decision trees is still used for more, I would say, professional situations, but we don't necessarily do that anymore here. Because it's interesting, but limited on many ways. So decision trees are hierarchical, are making hierarchical separation of the input space in a rather recursive way. So we kind of build the root and then we go and build all the leaf until the branches, the nodes, until we reach the leaf of the tree. So each node of the tree is a test. We are making a test. So basically, when we go in a node, we just say, we look at, I don't know, for example, variable x3, and we look at the value of x3 versus some kind of discrete outcome. So either there is something that we look at, but generally with real values, we are looking at the threshold and say if x3 is greater than some values. Yes or no. And if it is yes, we go on one branch of the tree. If it is no, we go on another branch. So that allows to make this kind of recursive separation of space. So as we go down, we perform a finer and finer division of the input space. So the construction is usually top-down. We start with the root that is making the first test on one variables, and then we go left and right according to the outcome of the test. And as we go down, the original training set is made smaller and smaller until we reach a point where all the samples are from the same class or about the same class, where we will just stop and replace the next node by a leaf where it will carry the decision for that when we reach that leap. To avoid over specialization, we are often making use of pruning. This idea of pruning is to say once we constructed a tree, we will just apply pruning to remove some elements of the trees to just make it more general because it is easy for a decision tree to capture every samples and being able to have a near 100% accuracy in training, but the generalization will be another thing. So it's useful also for interpretation. Decision trees are relatively easy to interpret. Many fields like in health, they know how to deal with that. This is something that they see often. So decision trees here, this is the illustration. We say we have one tree on the left side. So let's say that we have a test which is start greater or equal to 8.5, yes or no. If it is yes, we go left. If it is no, we go right. So for the left, we have a second case is start greater or equal to 14. Yes, we go again left. We are reaching a point where everything is absent here, kind of green. Likewise, if we go to the right, we have another test, is age is less than 4.5. Yes, same thing, we are in the green zone. Then otherwise, we go in the yellow zone. And so if we interpret that, just to make a quick interpretation of these things, if we say, how do we reach this leaf? We just say, yes, start is over 8.5, start is less than 14, age is more than 4.5, and age here is more than 9.2. So this is really going through 4 decisions to reach that leaf. We can see on the middle and on the right side the representation of the input space versus the decisions. In the middle in 3D, and on the right, the other regions are split between in the domain. So there are some problems with decision trees for classification. These classifiers have a low bias and a high variance. So for one training to another, there is some randomness in the process. We can have, I would say, very high variance, very lot of variations on the decision trees generated, even if the data set is the same or almost the same. And as such, we also have a high risk of overfitting because indeed these trees are really powerful, are able to really capture most of the sample relatively easily. And this is even the case when pruning is used. So a natural solution, it will be to make an ensemble of trees, or what we call a random forest, because if we are dealing with individual trees, many trees together are making a forest. So we are dealing with this random forest, where we will average a decision over many trees. That will allow us to keep the bias low while reducing the overvariance significantly. To achieve that, we should enforce that the ensemble must include a good diversity of trees. We don't want to get all the same copy, only a few trees. We need to deal with that with dozens, I would say even maybe hundreds of decision trees to achieve good results. And as such, we are randomizing the generation process of the trees with bagging and random subspaces. So for each node, when we build the tree, so for each tree, we just mask the set of data and the set of variables. By masking this, we have a much more narrow view, and we kind of train or determine the value, the configuration for that node, and then move on to the next element in the tree, again with this kind of randomization over the choice of sample and the choice of features. So this leads us to our random forest. where decisions are made by averaging the three decisions. And the variance on decision is a good indicator of our overall confidence, because if we have enough of those, still the variance can be there. And that variance is somehow giving us an information about how, I would say, unanimous are the models for assigning one sample to one class, or maybe they are diverging. If there are some divergence, then that means something else. That means we are not that confident over the decision.